Good morning, everybody, or mid-morning, depending on where you are. Yeah, I've got a kind of a group presentation here, just acknowledging the co-authors. We've got Peter Schwartz, Dolly Wang, Rupesh Shrestha, Michelle Thornton, Shiche Cao, Marcia Brandstetter, and Fengming Yuan have all contributed importantly to what I'm going to show you here. And the topic today is to give you a progress update on the project that we've had underway as an NGD activity in the Land and Energy NGD for the last year, trying to establish a capability to do very high resolution offline simulations over large regions. The resolution we're targeting is 1 kilometer resolution, and the region of targeting right now is North America. But the objective really for this is to be able to establish a capability to be able to do this kind of simulation at high resolution for other regions, including potentially global simulations, and eventually to be able to tie this into coupled simulations as well. But we wanted to start with something challenging but tractable. And so offline, 1 kilometer, North America was the objective. And we broke this down into 5 separate tasks over the past year, and just kind of giving you a quick summary of what those tasks are. And the colors indicate degree of doneness of these tasks after a year of work. The first thing that we tackled was to construct the high resolution surface weather forcings, including all the sub-daily downscaling that's needed to provide sort of our best quality of input data for the model over this region. We also have been assembling other high-resolution surface data sets, and this one's marked, this is task 2, marked as yellow because there are a couple of things that we have not been able to get together on our own in this time period, but we do have, we're reaching out to Teklu Tesfa and the group at PNNL, who have done some similar work with high-resolution surface data sets that we think we can complete all of the variables that we need by leveraging the work that they've already done. So that's something that we're still exploring a little bit. We needed to adapt the ELM model and its coupler bypass methodology to be able to run on a GPU system. The only way to do these kinds of high resolution simulations over a large region is to make use of some kind of a system with lots and lots of thread capability. And so GPU was the target that we're going after, and working on the Summit system was our target system. And I'll say quite a bit more about that in a minute. We do have that implementation complete, and also having to adapt the input and output methods to accommodate data transfer onto the GPU and data export from the GPU. That's all completed. And we are now in the process of executing some subsets of the North American domain and testing the spin-up runs for that. For these subsets, we're still, as you'll see, there's still some optimization work which is underway, and we don't want to jump on and use a lot of time on the machine for the full North American domain until we're sure that we have the best performance that we can and we think there's a little bit more optimization that we can do to bring the timing down further and make better use of the resource on that machine. So we'll show you kind of where that's all at. But I'll just start with a little bit of motivation to show you where we were prior to this work with our highest resolution offline simulations with the land model. So typically we're running on a half-degree grid. This is for the fully coupled carbon, nitrogen, phosphorus biogeochemistry in the land model, and just showing you the global grid at half-degree so you can see what that looks like. And I'll show you what the 1 kilometer grid over North America looks like compared to that half-degree grid, just to give you a sense of the additional detail that we are trying to achieve over this region first and eventually globally with this kind of simulation. So there's obviously lots of important detail that's not captured in the half-degree grid that we think we can capture with a 1 kilometer grid, including all the topographic effects, but as well as that, just details of the synoptic scale forcing that are missing at the half-degree. The picture on the left is the annual average maximum temperature for 2019, just one of a summary output from the surface weather forcings that we've developed for this project. And it's actually, you're not seeing it in this view at its full resolution. It's only about a quarter resolution. We blow it up to full resolution. It's bigger than you can fit on these screens. It's about 10,000 by 8,000 grid cells, the rectangular image there. And just to give you a sense of the size of the problem, the North American domain at half-degree resolution on the right is about 10,000 grid cells. That same domain at the 1 kilometer resolution on the left is 22 million grid cells. And so obviously, there's a factor of, in that case, about 2,000 increase in the size of the problem that we're tackling. And it's a capability that we've kind of aspired to for a long time, to be able to do this kind of high resolution simulation, but it just simply is not possible to do those runs in a reasonable amount of time on the current CPU enabled systems that we have. It would take on the order of 3 years of continuous simulation on one of our most capable CPU systems to begin to tackle this problem at 1 kilometer. So we're trying to get it faster than that and to be able to work on systems that we actually have access to. Just showing you another example of those surface weather forcings that we've developed. The surface weather is one of 5 tasks. We've done quite a bit of work to generate the best possible input data sets that we can. We've updated our methodology with all of the new station data that's available from various networks for 1980 through 2019. So we have multiple decades of high resolution forcing. We corrected a number of biases which we've known about or that we've discovered in both in this input data sets as well as the way that the input data sets are interpolated to the high resolution. So correcting time of observation biases in temperature, for example, correcting sensor biases from the high elevation SNOTEL data record, and then applying temporal downscaling to go from the daily observations that are common in these networks to the sub-daily inputs that we need for the ELM. And we've been using the GSWP3 forcings to extract some of the downscaling time information where needed. So that work is all complete. I'll just show you a little bit about what our computational strategy then is for being able to implement this approach on GPUs on the Summit machine. And first, just to give you a quick introduction to the architecture of Summit on the left, just to demonstrate or illustrating what the Summit nodes look like. There are 2 CPUs with many CPU cores on each of those CPUs. And there are 6 GPU devices, the NVIDIA Volta V100 devices on each node. Within each of those GPU devices, in the center figure, showing you that's broken up into multiple, what they're called streaming multiprocessors, or SMs. And each of these GPU devices has about 80 streaming multiprocessors, and those all share 16 gigabytes of memory. Within each of those SMs, there are then multiple different kinds of computational cores. And in the case of these Volta V100 devices, each SM has 32 double precision cores that can actually be oversubscribed with multiple threads per core. And our objective was to target the use of those double precision cores, meaning that there's a lot of other resources on the GPU. For example, the single precision and the integer cores and the tensor cores, which are not being used. But this simplifies the problem for us, because we don't have to try to come up with code that makes efficient use of integer logic. We can just stick with all the double precision logic that is native to the ELM model. Our basic idea is to do as little modification of the code as possible, and to explore the use of OpenACC as the programming model for implementing this parallelism within ELM. And specifically, we're looking at using the clumped parallelism, which is already native within ELM, to make a small number of grid cells reside on each one of these double precision cores, or each thread within an SM, and then use up all the SMs on a single GPU and treat that whole unit as a single MPI task. So we've done a lot of testing of that approach, and that does seem to be working well. I'll show you more details about that. But just to then drill down a little bit more into the detail of how this the MPI and the OpenACC are working together. Each GPU on a node has its own MPI task, so we'd have 6 MPI tasks per node. We are putting as many grid cells on each GPU device as we can, and that ends up being limited by the memory on the GPU device, so the 16 gigabytes of shared memory per device. And then at the CPU level, we're doing all of the inputs and outputs and staging data to the GPUs and staging data back off the GPUs to do, for example, history writes, restart writes, and reading of the input data sets. This particular slide indicates this NVMe, which is something that we're currently exploring, the use of the non-volatile memory component of Summit in order to speed up the import of the data sets. Let's see. Yeah, the other, I guess, salient feature here, we'll get into a little bit more detail later, but we're using the deep copy capability of OpenACC to transfer large chunks of data and then use the data kind of in its, as much as possible, its native ELM data structure format on the GPU, meaning that we minimize code rewrite in order to get effective use of the GPUs. So to make this even a little bit more explicit, within a single run, all the initialization and reading of surface data sets and so on is happening on the CPU at the node level, in the same way that it does in a regular MPI ELM offline simulation. There's a step where large chunks of data are then moved onto the GPU, and do that as few times as possible. And then the complete time step loop is executed on the GPU with all of the substeps which are currently defined within the ELM main time step. There are multiple clump parallel regions that are already existing in the ELM time step, and we've retained that clump parallel breakdown because it's actually important in terms of the science to be able to do things in a sequential order, but to have clump parallelism in each of those sections. So that's we've implemented all of that so that that clump parallelism is now being executed by the GPU threads. And so that was a big lift to be able to make that port and demonstrate that it was working correctly. And the way that we did that, and this is work that was based on early work by Dali Wang to develop functional unit testing frameworks, and then expansion on that by Peter Schwartz over the last year to be able to, as each of these, say, substeps or kernels was built up, we're using this functional unit testing framework to actually implement the code within a GPU framework and test and make sure that it was working correctly, and that we were able to identify all of the necessary data transfer points. And quite a bit of automation work was done by Peter with Python scripting to essentially parse the existing code and determine which variables and data sections needed to be implemented on the GPU. So that is a really nice piece of work that seems to have accomplished a lot in a short amount of time. I'm going to show you next some of the timing information, but basically what we see at a broad scale, kind of what we would expect, which is that it takes a significant amount of time to move data onto and off of the GPU. And the more grid cells, the more work you have to do on the GPU in terms of number of grid cells, the larger the data chunk is that you need to move on or off, and so the longer it takes. But once you have a big chunk of data resident on the GPUs, you can actually scale out to many, many grid cell simulations in parallel without really any additional time costs. So that's what these two plots are demonstrating on the left, just what you would expect that as you increase the number of simulation sites per GPU device, the amount of time it takes is going up. But as you increase the number of SMs that are engaged on the GPU to do parallel work, the amount of time it takes for a given number of time steps is actually the same. So that's good, and it means that there's very minimal conflict among the SMs as you scale out and fill up the device. Now, this is limited by, as I said, by the available memory. So we've done a lot of testing to go from tens to hundreds to thousands of grid cells per device. And it looks like right now we can get up to about 2,000 grid cells per device before running out of or running short on that shared memory. So that's still very good. That's about what we thought we'd get when we estimated sort of the number of SMs and the number of floating point cores per SM. We're getting close to what we thought we would be able to achieve in terms of occupancy on the GPU. This is just to make the point that as you move to doing more work in terms of more time steps between having to load data in and load data out of the GPU, we get the desired shift toward focusing the time, the computational time cost on the physics computations, chemistry and physics computations. So that's not surprising. It does have implications for if we were to implement this in a coupled system. For one thing, we'd have a much smaller data exchange needed, because right now we're loading 30 years of data into the GPU, 30 years of sub-daily time step data for 2,000 grid cells into the GPU, so that we can cycle many times without having to reload data. And that's what we tend to do for these offline simulations using the coupler bypass, just to get good performance. When we're doing a coupled simulation, of course, we'd have to refresh the driving data every atmospheric model time step. Then there's also been a lot of work to improve the performance of the history handler, so that you can actually run the full history update cycle on the GPU device, and then just copy things out at the, say, monthly history increment, and then let the CPU handle the writing to disk. I think I've covered a lot of this. As I said, we're getting about 2,000 grid cells per device with 6 devices per node. That's about 12,000 grid cells per node. And with 22 million grid cells, we could use about 1,800 Summit nodes out of the 4,600 or so that are available efficiently to run a problem like this. And that is what we would like to do, actually. At the moment, the timing is about 160 seconds per model day, which is only about 1.5 simulated years per day, which seems very slow until you compare that with if you were going to try to do 20 million grid cells on a CPU system. A, we don't even have a system that could do it, but B, if we did, it would be a massive system and would take about a year, about 3 years actually of simulation time to do a 200-year spin-up simulation. So where we are today with our performance tuning is that we can do a 200-year spin-up simulation on Summit in about 5 months. And that's much longer than we would like, but we're also still many opportunities to explore there for additional optimization. I'm going to talk about that in just a minute. And looking at our time here, doing okay. Yeah, the basic idea here is to be able to handle the OpenACC data directives. Each of the subroutines and each of the data types needs to be declared with some ACC directives, so that's not too invasive to the code. There are a few things that have to be changed in order to remove allocatable arrays and replace them with pointers, and that's actually a nice thing because it sort of enforces a consistent handling of the pointer logic throughout the ELM code, which we didn't have, and we didn't really have a good reason for selecting one way over another way, but now we do. So I would be suggesting that this is some way we can standardize in the future. And then each of the routines is, as I said, parallelized within these clump parallel regions, and relatively inobtrusive within the routines, but requires some changes in the way that the parameters are called for the routines. So I'm not going to go into all the details there, but basically passing slices of derived types arrays are not supported, so we use associate variables. And so that's a common thing already in the ELM code and just needs to be kind of enforced at places where it wasn't before. And in terms of performance optimization, we know that the dynamic memory allocation is much slower on the GPUs than CPUs, so we try to avoid that wherever we can. And at the moment, the optimization flags for the PGI compiler are not working. So we know that there's additional optimization that can be achieved, probably if we go to a finer scale, a finer grained use of the optimization pieces. So in the interest of leaving a couple minutes for questions, I am going to stop there and ask for your questions.